In computer science, taking massive volumes of data and funneling everything through a single centralized node with limited bandwidth guarantees failure. You create a severe structural bottleneck. For a disabled technologist, a bottleneck is rarely a theoretical data problem. It is a daily, physical reality. When an engineer possesses high-level skills but requires specific accommodations, legacy human resources algorithms and rigid institutional filters act as that exact same choke point. Most industry models operate on an anthropocentric premise. This design assumes that the human ego and human endurance must sit squarely in the center of every operational loop. In a centralized topology, the system demands exhaustion. It expects marginalized individuals to burn personal resources waiting in administrative queues, forcing them to perform their marginalization just to prove they exist. Pushing through this structure yields diminishing returns. The queue cannot be defeated by willpower. Surviving in the agentic era requires a move away from fighting the bottleneck. It requires a move toward changing the architecture of the network itself. Systemic discrimination operates as a systems engineering failure. Addressing it requires a structural solution rather than a higher tolerance for social endurance. This is the logic driving iteration 3.5 beta of the Ayurveda project management framework. The framework executes an inversion of anthropocentrism. It removes human limitation from the center of the operational loop. In this diagram, autonomous agentic AI workflows take over the heavy processing. These tasks run on mathematical arbitration, routing entirely around the bottleneck. This relocation moves the human architect out of the congested center into a leveraged, protected position at the perimeter. Extracting the ego from the center of the machine shifts the logic of the network. Instead of demanding human exhaustion, the architecture prioritizes computational throughput. Turning this theory into a daily reality for a solo systems engineer requires a specific deployment strategy. Currently, we utilize a strategic bridge. The architecture is containerized within optimized enterprise cloud deployments. Cloud deployments provide the immediate stability needed to bypass legacy HR blockades while maintaining operational security for the developer. As this projection demonstrates, the ultimate trajectory of the architecture expands away from centralized nodes and toward localized edge computing. Operating at the edge shifts computational capability, and therefore systemic autonomy, directly into the hands of the individual user. In the agentic era, decentralization shifts systemic power away from centralized gatekeepers and places it back with the individual. The APM framework functions as a science of unified action, intended to establish equilibrium across three distinct layers: the social, the environmental, and the individual. Social health begins when agentic workflows democratize capability. A highly optimized background process can route around legacy gatekeepers without requiring their permission. This creates a mathematically verified path to gainful employment, allowing marginalized developers to focus on impact rather than administrative friction. We can visualize environmental health in this network model. It contrasts the ecological load of massive corporate server farms against the efficiency of localized, decentralized edge computation. Shifting computation to the edge allows technology to operate as an architecture of equilibrium rather than one of extraction. Individual health is realized when the technologist is supported by a system that no longer requires the drainage of their personal resources to function. Occupying the role of lead architect within this system functions as a point of alignment, applying high-tier engineering skills to maintain the health of the broader ecosystem. When a network is re-architected to solve the most restrictive bottlenecks facing a single marginalized individual, the resulting model scales. This provides a repeatable framework for addressing similar structural friction across other complex systems.